Okay, I'm going to talk about empirical and molecular formulas. So first, an empirical formula and a molecular formula, those are just types of chemical formulas. So you have kind of these two different types that we can write. Now, most often what we write down is what we would call the molecular formula, but sometimes that could be the same thing as the empirical formula. But most often, really, what we're interested in is the molecular formula, whether or not that happens to be the same thing as the empirical or not. So, what a molecular formula is the actual number of atoms in a given compound, whereas the empirical formula is the simplest ratio of atoms in a compound. So, they are different with respect to the definition, but sometimes the formula ends up being the same, but lots of times it's not. But like I said, the molecular formula is usually what we want to know. So we usually want to know how many actual atoms of each element are in a particular compound. But sometimes just knowing the simplest ratio is good enough. But also when we do experiments to try to determine a chemical formula, what we come up with first is the empirical formula. And then there's ways to do further experiments to figure out the molecular from the empirical. We're going to look at just kind of the relationship between these two things and how we would go about finding an empirical formula from experimental data. Okay, so we won't do that final step of jumping from the empirical to molecular in this video. Okay. Um, when we're talking about molecular formulas and empirical formulas, it can be helpful kind of to look at some examples. So before we jump into the actual finding the formulas, let's look at some examples and comparisons of this. So if we have water, and we wanted to talk about what water is actually made up of, we would usually communicate to you that the chemical formula is H2O. And that really is the molecular formula. Okay, that's how many atoms are in each molecule. Okay, but if we think about the definition of empirical formula being the simplest ratio of atoms in a compound, that's also H2O for water. Okay, so the simplest ratio of hydrogen to oxygen we can get is 2 to 1. Okay, so it should be whole numbers. Okay, so when we talk about an empirical formula, it's the simplest whole number ratio. So you can make note of that as well. Now, another example for a molecular formula would be for hydrogen peroxide. The molecular formula is H2O2. So in each individual molecule, there's 2 hydrogens and 2 oxygens. Okay, but a 2 to 2 ratio is not the simplest ratio of atoms. The simplest ratio of atoms in that case would just be HO, so 1 hydrogen to every 1 oxygen. So that's a case where those formulas are not the same. Another example would be glucose. A glucose molecule contains 6 carbons, 12 hydrogens, and 6 oxygens. Okay? And so C6H12O6 would be the molecular formula of glucose, whereas a 6 to 12 to 6 is not the smallest ratio of atoms. 1 to 2 to 1 would be the simplest ratio because each of those 6, 12, and 6 can be divided by 6 to reduce them down to a smaller ratio. Okay, so CH2O would be the empirical formula of glucose. Okay, so it's just a scaled down version of the chemical formula. But as I said, most of the time we want to know them. But the empirical formula at least gives us some information. It does tell us, the ratio of elements, so the proportions of those elements that need to be present. If you calculated, say, the mass percents or the percent composition of these things from the molecular formula and from the empirical formula, you would get those same, you would get the same percent composition. Okay. And so when you look at just the proportions, they're the same, whether you want to talk about it in the scaled up version or the scaled down. So the molecular formula or the empirical formula. Uh, but as I said, most of the time, the reason we would talk about an empirical formula is because experimentally, that's the easiest to find. That's what you can find first. And once you have that, you can convert it to molecular. What you would need is to know what is that ratio between them, and that's tied to the mass, okay? So if there's a difference between the empirical and molecular formula, there's always going to be some factor that relates them. So between the molecular and empirical formula of hydrogen peroxide, there's a factor of 2, okay? And that's also going to match the ratio of the masses. And so if you added up the mass of H2O2 and the mass of HO, you would see that the mass of H2O2, the real formula, is double that of the empirical. Okay, so if you had the empirical formula and you knew the mass of the real compound, you could convert from the empirical to the molecular by figuring out what that ratio of masses is. But I don't want to focus on that here. I want to focus on the actual empirical formula and the molecular formula, what their general relationship is, and then just first finding the empirical formula. So again, to reiterate, molecular formula is the actual number of atoms in a compound. So you actually have these individual molecules that is what they're made up of. So water is really 2 hydrogens for every 1 oxygen. Every water molecule, okay? And hydrogen peroxide really has 2 hydrogens and 2 oxygens in each individual molecule, okay? Whereas if we're talking about ionic compounds, the one kind of unusual thing is, well, since an ionic compound consists of a lattice of cations and anions, so lots and lots of cations and anions, when we write the chemical formula of an ionic compound, it's written in the lowest ratio of ions to make a neutral unit. So we're not actually writing how many are in this huge lattice because it depends on what sample of that compound that you get on how many would be there. So by writing the chemical formula of ionic compound as the lowest ratio of ions, very often what you're writing is not only a molecular formula for that or considered to be the molecular formula, but it's also the empirical formula. So say when we have a lattice of copper 2 ions and oxide ions, we write down the formula of that as CuO, okay, which would be not only the molecular formula, but also the empirical formula of that compound, okay? Whereas if we have Cu plus and O2 minus in a lattice, that would be Cu2O would be how we write the chemical formula, which that would be the molecular formula, so the true ratio of those things, but it also is the lowest ratio that we could have, and so that would also be the empirical formula. Okay, so usually we would only distinguish between the terms molecular and empirical formula when we're talking about covalent compounds. Because that's usually the only time that you have a difference if there is one. But you can use that terminology with ionic compounds. It's just very often they're the same thing, okay? So with ionic compounds, we'll usually just stick with the term chemical formula, or if we're trying to figure out the formula, we'll do an experiment and find the empirical formula. And that should be the molecular for an ionic. Okay? If it were molecular, you would need to, after finding the empirical, use the molar mass of the true compound to find the relationship between the two. But we're just going to look at first quantifying or, using numeric data to figure out an empirical. So let's look at just the basic steps to give you kind of a method. Okay, so if we want to determine the empirical formula from some numerical data, there's kind of a four-step process that you always go through, okay? And step one of that process is to find the moles of each element, okay? Now, occasionally, you're directly given the moles. So if you're already told how many moles of each element are there, step one is done for you. But some other possibilities are maybe you're given the mass of each element. If you're given the mass of each element, you can convert that mass to moles using the molar mass of each of the elements, okay? And so that's one possibility. Another one is sometimes you're given a percent composition, and that means you would have to pick a sample size because a percent composition is just giving you a ratio, okay? It's put on a per 100 scale, so it's easiest to say, okay, well, if I have this percent composition, I'm going to say I have 100 grams of this. So then you can just change out the percents as grams, okay, of each element. And then you can convert them to moles. And then next, once you have moles, what you want to do is divide each of those values by the smallest number of moles. Now, the reason we do this is kind of a math trick to get whole numbers, or at least get some things into whole numbers, because the smallest thing when you divide by itself becomes 1. So at least one thing becomes a whole number. Usually all the other stuff becomes whole numbers, or something that is easily related to how you could scale it to a whole number, okay? Because the next thing you need to do is, if you didn't get whole numbers from that, is you need to scale them to whole numbers, okay? So for instance, you might come out with, one of them becomes a 1 and the other one becomes a 2.5, okay? And if so, well, 0.5, if you double that, it becomes a whole number, right? But you can't just randomly double something or triple something. You have to do that to all of the values. So you would scale all of them the same. Okay, so if you have something that has a 0.5, you would double everything. If you have something that has like a 0.33 or a 0.66, you would triple everything. Okay, because 0.33 is a third, 0.66 is 2/3. So by multiplying by 3, you would create whole numbers out of everything. Or if you have something like 0.25 or 0.75, you would multiply everything by 4. Okay, so you would scale things to where everything would then be a whole number. Now, when you do this, guys, you can be off by a little bit. Like if you come up with 2.99, now that's close enough to 3, that's fine. And so you would just round that. But you should be within, I would say, 0.05 of a whole number. If you're not, something's wrong, or you need to do some scaling, okay? And then the last step is to take those whole numbers you came up with and put them as subscripts in the formula, okay? They go as subscripts to each of the elements, whatever element that's the moles of, okay? And that gives you your empirical formula, okay? And if you're dealing with an ionic compound, that should also be the molecular formula. If it's a covalent compound, you would need the molar mass to jump between to figure out the factor, okay? So let's look at a few examples of going from experimental data of the breakdown of the elements to an empirical formula. So first I say determine the empirical formula of a compound that contains 5.60 grams of vanadium and 4.40 grams of oxygen. Okay, so I have those two masses, and my first step is to convert my values to moles. So I'm going to take the 5.6 grams of vanadium, and I'm going to convert that to moles. I'm going to do dimensional analysis. Grams of vanadium opposite, so on bottom, so it'll cancel with that grams of vanadium that's on top. And I'm going to convert it to moles of vanadium. So to relate grams and moles, I look at the periodic table, and vanadium is 50.94. Okay, grams per 1 mole. And then, let's see, 5.6 divided by 50.94 is 0.1099, and I always keep an extra sig fig as I'm doing calculations. Okay, and then 4.40 grams of oxygen. I want to convert the grams to moles. Okay, so I look at the periodic table, and it's 16.00 grams for every 1 mole of oxygen. Okay, so my grams of vanadium canceled there, my grams of oxygen is going to cancel. 4.4 divided by 16.00, and that gives me 0.275, and it happens to be that exactly. I'll just tack on the 0 there. Like I said, I keep extra sig figs throughout just to make sure it doesn't introduce any excess rounding error. You round too much when you're trying to do an empirical formula, you'll never get to whole numbers, okay? Or it might throw things off and you'll come up with the wrong numbers. So that's step 1, we figure out moles. Next step is divide by the smallest. So we have 0.1099 moles vanadium, okay, and we have 0.2750 moles of oxygen, and we divide each by the smallest. So we're going to divide each by 1099 because that's the smallest number of moles, okay? So I'm going to get 1 mole of vanadium, and I'm going to get, let's see, 0.2750 divided by 0.1099. That comes out to 2.502 moles of oxygen, which basically is pretty close to 2.5 moles, okay? So that makes it a little easier to look at. So I've got 1 mole of vanadium for every 2.5 moles of oxygen, right? It's within 0.05 of 2.5. So that's safe to round to that. You can't round the 2.502 to 3. That's way too far from 3, okay? Now I need to scale it to make it whole numbers. So if I had 1 mole of vanadium, every 2.5 moles of oxygen, I can multiply each of those by 2, okay? So whatever I do to one, I have to do to the other once you're in moles. And so that would give me 2 moles vanadium or 5 moles oxygen. So now I have whole numbers. Those go as subscripts in my formula. So it'll be V2O5. Okay? Okay, and let's follow this process for at least 1 more. I think I have 2 more actually for it. Here we go. So determine the empirical formula of a compound containing 30.45% nitrogen and 69.55% oxygen by mass. So remember I said if you have percents, you can just convert those to grams because each of those is per 100 gram of sample. So really 30.45% of nitrogen by mass is 30.45 grams of nitrogen per 100 grams of our sample, okay? And 69.55% oxygen would be 69.55 grams of oxygen per 100 grams of the sample. And so I can just say, okay, well, I'm going to figure out the formula for a 100-gram sample because it doesn't matter what sample size. The chemical formula of a compound doesn't change if you take a different amount of that sample. Okay, I could take 100 grams of that sample, 5 grams of that sample, 23.2 grams of that sample. It does not matter. So to make my life easiest, I'm going to say, okay, if I had a 100-gram sample, that means I have 30.45 grams of nitrogen, and I have 69.55 grams of oxygen. Okay, so then I'm going to convert those each to moles. So I'm going to get rid of grams of nitrogen. I'm going to go to moles of nitrogen. So I use the periodic table. Look up the molar mass. It's 14.01 grams per 1 mole. Okay, I would do the same for oxygen. I want to get rid of grams of oxygen. I want to go to moles of oxygen. So 1 mole is 16.00 grams. So that's each going to cancel grams and give me moles of those things. So 30.45 divided by 14.01 is going to give me 2.174 of nitrogen. Okay, so I'm keeping an extra sig fig. You always want to keep enough sig figs where it doesn't throw in a bunch of rounding error. Usually means one more than what you were given until you're at your final answer, okay? Or in this case, until you get into your whole numbers. So let's see, this next one comes into 4.3469 moles oxygen, okay? So then I'm not going to rewrite those. I'm just going to tack on here. We're going to divide by the smallest, so divide by 2.1734, and we're going to divide this one by 2.1734. And when I do that, I get 1 mole nitrogen, and then 4.3469 divided by 2.1734 gives me 2.00000 moles. And then after that fourth zero, there's a digit, but that's okay. Remember, we should be getting somewhere close to whole numbers, so that's close enough to 2. Okay, it's within 0.05 of that. Okay, so that directly is whole numbers. I don't need to do any scaling at this point, so I just put them as subscripts. So NO2 would be the formula, or the empirical formula, I should say. Because in this case, that is 2 nonmetals. So NO2 is the empirical formula. It may or may not be the molecular formula. Whereas on the previous slide, we had vanadium and oxygen. That was a metal and a nonmetal. Usually that then is not only the empirical, but the molecular formula. Okay. Okay. Now let's look at one more, a little bit trickier. Okay. This is a little closer to the type of experimental data that you would likely collect. Okay. And so for this one, I say we take a 0.87 gram sample of boron, and it reacts with oxygen, and it forms 2.802 grams of the oxide, meaning of the boron oxide compound. So what you're doing is you're taking a boron sample, you're adding it to oxygen, okay, and you're forming some boron oxide, okay, and we want to know what that compound is. And so from that, we know that we started with 0.87 grams of boron, okay, and we produced 2.802 grams of the oxide. And so to find the empirical formula of that, we need to know the amount of boron and the amount of oxygen, right? Because we need to convert each one of those to moles. You weren't given the amount of oxygen, but based on conservation of mass, those need to, the reactants and the products need to be equal. So what you started with and what you end with has to be equal. So that means that however much oxygen we had has to sum with the boron and equal 2.802. So I can take the 2.802 and I can subtract the 0.87, and that tells me that I must have reacted this with 1.932 grams of oxygen. Okay, that's the only way I could get 2.802 grams of product. Okay? Now, another way you could do this type of experiment is we could have taken the boron oxide and broken it down, okay, into the two elements. And no matter what, if you do this type of experiment to find empirical formula, conservation of mass has to hold true, okay? So your individual components must sum up to your total mass of the compound. Okay, but back to getting the formula. So now I know how much boron I have and I know how much oxygen, and I need to get those in units of moles, okay? They have to be in moles to figure out the subscripts of the formula. So I have 0.87 grams of boron, I have 0.932 grams of oxygen, so I need to convert each of those to moles. So grams of boron to moles of boron, right? Put my grams on bottom so it cancels. I look at the periodic table, and boron is 10.81 grams per mole. oxygen, I put grams on bottom so it cancels, and moles on top because that's relevant. And look at the periodic table, and we have 16.00 grams per 1 mole. So then if we type that in the calculator, oops, go 0.87 divided by 10.81 gives us 0.08048, which should be way more figs than I really, that's okay. More than enough is better than rounding too much. Okay, 1.932 divided by 16.00 gives me 0.12075 moles of oxygen. Okay, so I have moles and I want to get them into whole numbers. So first divide by the smallest. So I'm going to divide them both by 0.08048. Okay, 0.08048. So that's going to give me 1 mole of boron, okay, and then 0.12075 divided by 0.8048. That gives me 1.5004 moles of oxygen, okay, and so that's pretty much 1.5 moles of oxygen, right? It's within 0.05 of that, so that's good enough. And so I can take the 1 mole of boron, 1.5 moles of oxygen, and I can multiply those both by 2, and that will make them into whole numbers. You can't just round that 1.5 to 2. It's too far from there, okay? So if you multiply both of them by 2, you would get an empirical formula of B2O3. Okay? Okay, so that's the basic idea of how you would get an empirical formula. Now, as I said, if it's a molecular compound, you know, it's possible the molecular, or that's the empirical. If it's a molecular compound, the molecular formula might be different. And so if you had the molar mass of the real compound, you could divide it by the molar mass of the empirical formula that you found, okay? And then you would get that whole number factor. So if the masses are equal, the empirical and the molecular formula is the same. If the molar mass of the real compound is double, then you would double all the subscripts. If it's triple, you triple all the subscripts. Okay. So that's how you would do that. I'm not going to do any of those calculations because that part should be pretty logical. Hard part is finding the empirical form. So now hopefully you've got an idea of how to do that.